Well, I'm going to show everybody our PDHP website here. Just sharing my screen. Okay. Okay. So, right, welcome everyone. Again, like Paul said, sorry for the technical mix-ups this morning with the link that was sent out with the registration email. So everybody should be able to have access right now. And again, you can remind your colleagues if they had a hard time getting in that they should have no problem clicking on that link right now. Like Paul said, my name is Brady West. I'm the director of the Scientific and Technical Core that's part of the Population Dynamics and Health Program, or PDHP. This is the program that is offering today's workshop with Indira. So I'm really happy that all of you are here and joining us today. A little bit about background in terms of PDHP. This is supported by a research infrastructure grant to the Population Studies Center at the Institute for Social Research at the University of Michigan, Ann Arbor. That's where Paul and I work. And this center is supporting these types of research infrastructure activities, such as today's workshop, as a part of helping to develop population science researchers and equipping them with new tools to make meaningful research contributions, especially in this era of AI that we're going to be hearing about a lot today. So very important workshop for the times that we're working in. And again, we're very happy that so many of you have decided to join us today. So PDHP regularly offers these types of workshops through this research infrastructure grant, and they're always free of charge. So in addition to that, we record all of the workshops. So today's workshop will be recorded. And up on the PDHP website that I have displayed here, you can see that we have a link to a YouTube playlist where you can go and take a look at some of our past workshops and see some of the different content, some of the different methodologies that have been discussed in prior workshops if you're interested in some of our other offerings. We also have a number of other workshops coming up over the summer months and leading into the fall. So you can stay tuned to our workshops tab here at the PDHP website to stay aware of upcoming events in this particular area. We also offer the opportunity to work with our statisticians and data scientists via supported research projects. So if you have funding available for research and you're interested in getting some assistance with data analysis or methodology or research design, whatever the case may be, Paul, myself, or other colleagues, we would be happy to work with you to talk about these kinds of projects. So you can reach out to either of us, and we'd be happy to discuss possibly setting up a subcontract or something like that. If you'd like additional assistance with the research that you're working on and you have some support for that research that could be used for this kind of analysis support or design support or whatever you might need, please don't hesitate to reach out to us, and we'd be happy to provide that kind of technical assistance. Okay, so that's a big part of what PDHP does as well. But I just want to give everybody access to this website. I'll put it in the chat as well, so you can take a look at it at your leisure, see if there's any questions that you might have. But you can take a look at some of the other services that we provide, again, via this research infrastructure grant from the NICHD at NIH. So we want to acknowledge them and thank them for that support. Okay, so again, today's workshop will be recorded. So if you or your colleagues have to leave early or miss parts of it, the recording will be posted on our YouTube playlist, so you can always come back to that. We're also going to make all the materials available, so you'll be able to see the slide deck, the code, all that kind of good stuff. That's all going to be available via our workshop website. And we've already included that website in the chat as well, so you can click there easily. Okay, so without any further ado, I'd like to introduce today's speaker. I'm going to stop sharing my website here. Okay, so today we're joined by Dr. Indira Sen. Indira is a junior faculty member at the University of Mannheim's Business School and the chair of data science for the social and economic sciences. Her work lies at the intersection of natural language processing and computational social science, specifically in developing and evaluating representative and equitable language technology, including the topic of today's workshop, large language models. So Indira, we're very happy to have you with us today and looking forward to your presentation. At this point, I will turn it over to you, and you're welcome to share your slide deck and everything else. But thank you again for doing this, and we're looking forward to the workshop. So.
Fantastic. Thank you so much, Brady, for the kind introduction. Thanks, Paul, as well, for all the setup and coordination. Yeah, I don't think I've given a workshop with these many participants on this topic, so that's very exciting. Um, yeah, I think let's get started. Maybe before I share my screen, I will just put up the link to the materials as well. So these are, so this link is going to point to a Google Drive folder. I hope everybody can access it. If you can't, just let me know if you're getting an access error there or not. But yeah, essentially, this link should take you to a Google Drive folder that looks like this. It just has two subfolders in there, slides and notebooks. So the notebooks we will use in a bit when we get into the practical hands-on parts, but we'll first get started with the slides. So this is the main slide deck, and then there's this one which was a bit of preparation, although that's not mandatory at all. You can still follow along what I'm showing. And if you haven't done this, it's something that you can try out either in one of the breaks that we will be having or afterwards, so that you can do some parts of the hands-on lecture or exercises, right? Most of it should work, but for a few of these things, you would need to have done whatever was in the preparation. I can see a lot of unknown people popping up on the slide deck, so I'm going to assume that the access worked in that case. So again, if it didn't, just please do write on the chat and we can figure out the settings. But looks like we are good to go. Okay, then let's get started. So the topic for today is social science research with large language models. Let me try to put the Zoom thumbnail in such a way so that it doesn't block the content on the slides. Um, and in terms of logistics, I would just suggest that if you have any questions, please feel free to interrupt me. Like you can type on the chat, I'll keep an eye out on it, and you can also raise your hand and then unmute and let me know your questions or comments. So materials I already shared. In terms of what we're going to cover today and timing. So yeah, I'm based in Germany, so that's why it's 3 p.m. I understand that it's 9 p.m. Sorry, 9 a.m. there. That would be a rather late workshop if it was on at 9 p.m. So you can just subtract all of these numbers by 6 hours. If you're in Michigan, of course. If you're in other places, then do that accordingly. So we'll first start off with a 1 hour session talking a bit about the background on large language models and try to understand how these types of models were created. Like these are quite complex feats of engineering, and we'll try to see a bit of how they came about to be. Then we'll have a short break, and then we will go into our case studies where we use large language models for content analysis and survey responses. And then hopefully, if we have a bit of time, um, we will talk about biases in these LLMs that can reduce the validity of their application for social science research. Okay, so yeah, I will skip this slide because we already did the introduction. Um, so with a little bit of background on where I come from, because I understand that maybe many of you are health researchers or working on surveys. I'm a computer scientist, and we were interested in text mining, particularly, and applications of that to social science research. And to complement traditional data in social science research, such as surveys, experiments, observation, or interviews with newer forms of data. So, particularly what is often described as digital trace data. So, this is an example of digital trace data being created on digital platforms like LinkedIn or Google or Twitter, which is now called X. So people basically creating a lot of content on that, such as posts or connections or engagement with other types of content that leave traces, right? And we can learn about people's behavior from these traces. And so the methods that were previously applicable for traditional types of social science data might not always be applicable here, right? So perhaps these new forms of data require new types of analysis. And so that's why we started out. And then there was this entire area of computational social science, which discussed using digital trace data for social science research. And this new area of computational social science was born. And in terms of the method specifically, um, machine learning and natural language processing really gained a lot of traction over here. So one of the main advantages of this type of data was that it was available on really large scale. And that meant that we needed to scale up our content analysis pipelines, right? So that's where things like machine learning and NLP came in really handy to give us some type of automated or semi-automated approaches. And so I'll talk a bit about content analysis as an example, because again, that's like really widely used. Even when we think about using surveys, um, when we do surveys, we also have some open text answers available to us, right? And we might want to do some content analysis on that to try and understand the rich free text responses that people are giving to survey questions. And so the types of questions content analysis can help us answer are quite varied, especially when we think about social research, right? Like they can tell us about how the media frames particular issues. So, for example, how the news media represents an immigration crisis or even creates a crisis like framing. And then if we talk about a totally different type of data and different type of research question, we could analyze um, relationships and discussions or behaviors in relationships to understand what type of topics lead to arguments in these relationships. And finally, public opinion is very important to study. And we could try and see how the public, citizens perceive the performance of politicians during crisis times, right, such as pandemics. And so here in green, I've highlighted some of these examples of newer forms of data or digital trace data, such as news articles or social media posts from Reddit. So, for example, there is the subreddit called r/relationship advice, where people talk a lot about um, their experiences in relationship, asking for help. So we could potentially use that data to learn about this research question, and then we can use other types of social media data to understand citizens and public's opinion about public figures or politicians. And so, in terms of the pipeline, and if we get into like really how to do this type of content analysis, to take a broad approach, there are these two pipelines that we often think about. One is an unsupervised pipeline. So here ML stands for machine learning. And so we use unsupervised machine learning models to do some type of data-driven analysis. So this is usually quite bottom up, where we have some data and then we apply some algorithms on it. And then we manually assess that, maybe using by talking to an expert. And then we get some insights from there, right? So, in that sense, this is a bit more lightweight. The only part that requires a bit more effort is this qualitative assessment, right? Um, and then to contrast that, we have the supervised machine learning pipeline, which is a bit more complicated and requires more resources. Which is that because this is supervised, we require some labeled training data to create our algorithms or models, right? And for this, we require manual annotators to already have some content annotated. Um, and that can be a bit more time consuming and requires resources. Generally, this manual annotator set consists of people who are either crowd workers, like from certain crowdsourcing platforms like Amazon Mechanical Turk or Prolific, or they could be research assistants that have been or who have been explicitly hired for this task. All of this was happening before LLMs came into play. And especially since ChatGPT came out, things took a bit of a turn. There was this particular paper that seemed to claim that LLMs can outperform crowd workers in annotation tasks. And so, since then, at least this supervised pipeline has undergone some differences, right? So, it used to be that we had manual annotators for labeling a lot of our content, but now we can maybe use large language models to do that instead. And this is not just restricted to content analysis. Large language models can help in social science research in other ways as well. So here we have two papers that exemplify this almost new type of research where we talk about highly realistic or potentially highly realistic simulations with large language models. So, this paper talks about how we can get something called silicon samples or simulations of human samples, where we can ask an LLM to emulate people and behave like them and make them answer survey questions, make them participate in certain experiments, like psychology experiments that we would typically do with people. And we can glean insights about human behavior from these silicon samples. And it's not just surveys or behavioral experiments, it goes even further because there was this paper that tried to do simulations of platforms entirely, right? Which is important because we want to know when we are designing particular platforms, for example, a social media platform, will it become um, toxic after one point of time? Will people just start having lots of conflicts with each other? Will it be overrun by conspiracy theorists? What are the types of interventions we can design so that this type of antisocial behavior does not happen? These types of experiments would be hard to do in real life because of a lot of ethical issues. But we could potentially do that with highly realistic agents of that are human-like, right? And if we can show that these agents display certain levels of human-like behavior, then we could potentially get a lot of useful insights from these simulations. So that's kind of the background over here about why we might be interested in LLMs in the first place when it comes to social science research. And now I will go into a bit of the background on how we came to creating these large language models and why we think that they are powerful enough to be able to emulate people, right? Um, Maybe I will also, I know there are lots of people in the workshop, so we probably can't hear from everybody, but I'd be curious to know how some of you are using LLMs in your research already. So if that's something that you feel comfortable sharing, I would be really happy to know. Maybe you can put this in one or two sentences in the chat, so that I also get a sense of what type of experience people already have in the group. Okay, but then let's start with how we created large language models in the first place, right? So perhaps some of you are familiar with this first screenshot. I'm gonna turn on my laser pointer. So this screenshot is an example of an interaction that people had with a chatbot called Eliza. And this was actually one of the first chatbots ever created back in the 60s or the 70s. And so the screenshot is like kind of obscured by the other one from ChatGPT, but you can still play around with Eliza. It's still in the same setup as it was like 20 years, 30 years ago. Um, and so here you can kind of see how rudimentary this is, right? And you can contrast this with the experience we have with ChatGPT, which has so many differences. Like it just seems to give very coherent responses, at least like grammatically, the English almost seems to be perfect. And it just seems to display this high level of comprehension, right? Whereas you can see in this chat, the turn taking and the conversation is quite alien. And so we've like made leaps and bounds in this language technology, right? Where we started off with something like this and have come to something like this in the end, with a model that seems to have like a extremely strong grasp on human language. So how did that happen? So that a lot of these advances came from the field of NLP, which is about trying to make computers understand human language and be familiar with human language and behave naturally when prompted with human language, right? And so there are lots of neighbors of NLP. There's like all of this work on computational linguistics, and social sciences plays a big role. For example, particularly social linguistics, where we talk about whether language technology is equally good for people of different types of dialects. Multilinguality here is very, very crucial. Perhaps you've seen, if you've interacted with ChatGPT in a language other than English, that the experience is perhaps not entirely the same. So the social sciences have always have always played a strong role in NLP and continues to do so. And so, yeah, here is the full example of this conversation with Eliza. And we'll talk a bit about the timeline of NLP without going into too much detail. And so at the beginning, we had a lot of like these statistical rule-based approaches, which is also what we see in this example with Eliza, and then a lot of machine learning took over, and especially deep learning, right? And that has to some extent given rise to these modern large language models like ChatGPT that we see. Yeah, this is more of the same. So we'll first talk about what it even means to model language. So when we say we want to model something, it means that we want to mimic it or to create a smaller, less complex version of it so that we can study it and then predict future behavior of that model. Um, and so here you can already see that this aspect of predicting future behavior, studying the model, all of these kind of relate very much to some of the social science use cases that I talked about, right? About simulating behavioral scenarios with LLMs. Okay, I can see some content in the chat. I'll just check if any of them are questions. Okay. Nice. I think I see a lot of examples about programming, but also content analysis. Um, cool. No, that's super helpful. Here, maybe then another follow-up question would be that which type of LLMs you use, like ChatGPT, Claude, open source ones. So those of you who already said some of the tasks that you do, particularly things like psychology vignettes and crowd coding, I'd be curious to know which types of LLMs you've been using and how that's working out for you. Okay, so going a little bit more into depth about language models or language modeling, these are models that assign probabilities to sequences of words. Um, and so here I say words, of course, this is a bit more complicated depending on the type of language that we're using. So maybe the better technical term here would be any type of language tokens. But to just keep things simple, these are models that assign probabilities to sequences of words. And so language modeling is useful for lots of different things, and probably one of the most important and early use cases was machine translation, which was to automatically translate content from one language to another language. And for this, we really need language modeling, then also other things. And right now, when we look at this list, it seems that something like ChatGPT could do all four. But for the longest time, people in NLP were basically building custom tools for each of these, right? So you had one method for machine translation, like Google Translate, right? That's the whole idea behind Google Translate, to just do machine translation. Um, and again, going a little bit more into the technicalities of language modeling, when we say that we want to assign probabilities to words and tokens, the idea is that, let's say I already have some text like this. I saw a cat on. Um, and as a human, we can see that probably something that comes after this is going to follow a certain type of pattern. And so here, you can intuitively understand that I saw a cat on the versus I saw a cat on sun. Um, they have different probabilities, right? So something like the has a higher probability of coming here than sun. And so that's the whole idea of language modeling, which is that we go step by step and see what is the probability of all of these tokens or word combinations occurring together. And we can basically really use mathematical tools to be able to model that. So particularly probability theory and like the chain rule. And so here we'll take a bit of a detour and talk about machine learning. So machine learning and natural language processing nowadays are quite similar to each other, but that was not always the case. Machine learning is more the field of the study that gives computers the ability to learn somewhat automatically without being explicitly programmed to do this. So I saw that some of you said that you were also using LLMs for programming. So that is not machine learning. In machine learning, a model is supposed to learn on its own without being programmed to do so, right? And so one example that affects all of us in our lives is using our mail servers and our mail programs, which classify whether the content in our email are spam or not, right? And this is an example of machine learning. And so in machine learning, we have mainly these two branches. I already mentioned this when I was talking about the content analysis pipeline. So we have supervised machine learning and unsupervised machine learning. And so in supervised machine learning, the whole idea is that we have labeled training data, right? So regression is a classic example of supervised machine learning. And then we have classification as another counterpart. The difference between regression and classification being that here we're predicting a continuous variable and here we're predicting categories or discrete outcome variables, right? And so coming back to text classification to again see the relationship between machine learning and NLP, text classification is one of the most basic and popular NLP tasks, and it's going to have a lot of connections with what we're doing in this course or this workshop, and many connections to content analysis as well, right? So here we can see the spam classification. This is an example of something that we will use in our hands-on sessions. This is sentiment analysis, which is again a very, very classic NLP task, which is to see some type of content and say what sentiment it has, whether it's positive, negative, or neutral. And then we also have tasks like this, which is that if given a piece of, given a news article, you're supposed to say what type of topic it is related to. So more formally, the task of text classification is that given something, a document, a number, a set of numbers, we are supposed to classify it based on a fixed number of categories. And so here, numerical things are easy to classify because computers know numbers. But when we have words, that's a little bit harder, and we need to create a representation, right? And this representation is supposed to be something that computers can understand. And this pipeline of having a representation and then having a classifier, um, this is standard. Like, so this is something that probably your basic classifier is doing, but it's also what ChatGPT and these other sophisticated LLMs are doing as well, which is that when you write some content to these LLMs, like the prompt, that prompt gets converted into a representation, a numerical representation that is then given to the underlying model. These LLMs, of course, they are not just classifiers, but we will also use them as classifiers. But yeah, so coming up with this representation is vital. And again, to describe this a bit more formally, here the idea is that we take in an input X, which can belong to a set of output classes. Here we have M output classes. We are supposed to return the predicted class. And if I'm talking about NLP over here, X here is a document that we're going to use as our input. And so for supervised settings, we will have a training set of N documents labeled with the class. So this is what the type of labeling that potentially student assistants have done for us or crowd workers have done for us. And then we can learn a classifier that can scale this up, right? And so how do we obtain this numerical representation? And so here we'll start with the most basic version of it. So this is called a bag of words classifier. And so here the idea is that, let's say I have a document like this, which is a movie review. That's going to be converted into what here literally looks like a bag of words, right? Because the fundamental assumption here is that word order does not matter. The only thing that matters is which words are in there. Of course, this is very, very rudimentary and basic, right? Because, of course, word order is important. Maybe you can think about the types of use cases where word order is vital and your classification might depend on it. And we can chat about this in the break. Um, but yeah, this was one of the most simplest representations that we can create. And here is a concrete example of that. So let's say I have one document. The child makes the dog happy. The dog makes the child happy. And then if you convert this into a bag of words representation, we will basically create a matrix like this where we have the words on top and the two documents as our columns. And we will assign counts, right? The number of times a particular word occurs. And so here you can see that these two documents are going to have the exact same representation, even though they don't mean the same thing, right? The thing is, though, is that for certain types of classification, this directionality of who makes whom happy is not so crucial. So, for example, if you're just doing sentiment analysis or topic analysis, here we just care about which words are in there. Um, but for sentiment analysis, the word order can still sometimes cause problems. And so maybe that's something to think about. And now that we know about how to create this representation, and we will see, we talked a bit about also this language modeling. And I'm sure many of you know how regression works, right? Like we have this optimization function over there, which tries to learn the parameters of our model, right? So that's how text classification would work. Um, but how do we know if our classifier is good, if it's actually doing what it's supposed to be doing? Um, and now we need to talk about something that's really critical in machine learning and NLP, which is this idea of a train test split, right? That we have our data that we had annotated, and we split a bit of that into a training data set, which is used to train our models, and then a bit into test set. And it's really important that these two pieces of or these two data sets have nothing in common, right? Otherwise, we would be leaking information from the training data set to our test data set, and that would be pretty bad because then our model would would seem like it has a very high performance when in fact it doesn't, right? And it's not going to be a realistic measure of model performance. Um, and so, yeah, so we split our data into training sets and test sets, and then we do the actual evaluation. And here things get a little bit more complex because there are lots of different types of evaluation metrics. So some of you mentioned that you were also using content analysis. And so what type of metrics do you use to validate whether your LLM is working well or not? So maybe that's something that you can put into the chat. Um, I will mention those that are particularly popular. So there's accuracy, where we just see how many times we got the right answer over total answers. And then there are more complex metrics like precision and recall, which depend on whether certain classes are more important than others or not, right? Especially if you have highly imbalanced classes in your data. So yeah, this is a bit about the theory of text classification, and now we're going to use a more concrete example talking about sentiment analysis. So, sentiment analysis is the task of automatically annotating the sentiment or polarity of a piece of content. It used to be highly lexicon based. Um, and lexicon here means like dictionaries where we would have lists of positive words and negative words. And then we could just match which word occurred in my document and assign a value based on that. And then we started building machine learning methods using movie reviews, particularly. And movie reviews here were kind of like a win-win situation because you just had a lot of them available because people were rating movies online. They would give in a piece of content as the review, and then you would have a star rating, right? And so then you had a naturally labeled data set that you could use to train classifiers. And so this is a visualization of search queries on sentiment analysis over time. And you can kind of see that there was a large growth in this somewhere around 2008. Um, so do some of you have any intuition about why this picked up in 2008? And then from there onwards, it kind of kept growing. Again, so something that you can put in the chat if you have any thoughts on why sentiment analysis became particularly popular around 2008 or so. Um, yes. Rise of social media. The availability of a large amount of social media content and web content basically meant that we could now use that data for analyzing um, people's emotions and sentiment. And in fact, a lot of like companies still have these social media listening centers where they try to see how their brand is being perceived on social media. And this was one of the first papers that actually used social media data, like in this case, Twitter data, to try to see if they could mimic public opinion measurements that you would usually have via surveys with social media instead. And so this paper already came out in 2009 or 2010. And at that time, they seemed to say that for both presidential elections and the economy, you could see some alignment between surveys and social media data. So yeah, in that sense, sentiment analysis can be pretty useful, right? And in terms of the technicality here, it can be something as simple as counting the number of positive and negative words as you would do in a dictionary. The measure that you end up with is a bit more complicated. Again, if those of you here do surveys, you are probably familiar with the intricacies of this, right? Of designing a good scale for sentiment. Um, and so in this case, in this workshop, we will see a few different examples. But sentiment analysis kind of really exploded after one point of time. And this was one paper that tried to create a benchmark of comparing different sentiment analysis methods. Okay, I'm sorry that these screenshots are a bit grainy, but essentially they tried something like 14 different methods, many of which still exist. Like this paper is almost now 10 years old. Many of which still exist, right? And one example is called Vader. Um, so Vader stands for Valence Aware Dictionary for Sentiment Reasoning. Um, and here, this was basically a sentiment dictionary with a pre-processing engine that was particularly honed for social media analysis. And even though this paper is now like 10 years old or something, Vader is still very widely used, also because it's quite accessible. So that brings us to the first hands-on session that we want to try out. Um, and so here I'm just going to go back to the Google Drive folder, and I'll post the link to that again for those who came in later. And so, yeah, if you go into notebooks, there are 4 notebooks over here, and the one that we're going to start out with is this one, NLP Basics. So you don't have to follow along, but yeah, you can try this out on your own if you're interested, or you can just see what I'm doing on my screen. But here, the idea is that we are going to use Google Colab to set this up. Um, so all the hands-on parts are going to be done in Python. Um, Python is like quite popular nowadays, especially when working with large language models. So I thought it made sense to try to demonstrate these models using Python. So this might depend a bit on how you're using Google Colab and if you've used Google Colab in the past. But basically, the idea is that you go to this folder and click over here, and then it should show something like this. And here you can try to open this with Google Colab. And if you do that, then you should end up with something like this, where you have the notebook that I'm using, or the notebook that I've created, and you can basically now run this on your own. Um, so can I maybe see a quick show of hands of how many people are trying this out on Google Colab? So you can use yeah, the Zoom functionality to raise your hands. Okay, locally is also fine. So yeah, basically you can download the notebook, and yeah, if you already have a Python setup, you're familiar with Python, then you can run that yourself on your own computer. That is perfectly fine for this notebook, NLP Basics. That should not be a problem. For some of the other notebooks where we need better compute, that might be a problem, but we can cross that bridge when we get there. Okay, so great. Thanks a lot for those who raise their hands. I'm going to assume that you're following along with Google Colab. Maybe you can put your hands down, and you can already start running this. Here you would have to connect Google Colab, and that might take a bit of time. And as soon as you have a runtime connected, you should be able to um, run the stuff on here, which is you can click on this and run it. So I will just take a pause here to see if anyone is having issues with opening this on Google Colab or in their own systems. But for those of you for whom it already started, maybe you can already start taking a look at this notebook and read the documentation in there. Okay. Um, can I ask those of you who are having problems accessing this on Google Colab to raise their hands now? Charles, you have your hand raised. Are you having problems?
No, just forgot to lower it after the
Okay,
voting.
no, great. Okay, so let's see how things are going. Okay, yes. So the way that we do this, to open this on Google Colab, so this is the folder, right? So you go at the very right end, and then you click on more actions, and then there's open with, and Google Colab should be there. Sometimes it's not, and in that case, you actually have to open Google Colab yourself. So I will put a link to that. So you have to open Google Colab yourself and then go to new notebook and load this notebook that I just mentioned. Sorry, let's go back again. So this is the example, and now you go to upload, and then you have to basically download the notebooks in my directory and upload them over here. So for all of this, like the main and the only prerequisite is that you have a Google Colab account, and that should work out. Okay, and again, if it didn't work out for you, don't worry. This is something that we can also sort out during the break. Okay, so then let's get started. So we'll do some sentiment analysis ourselves. So I saw some of you already mentioned that you're doing content analysis with LLM, so this might be a bit boring. But still, I hope some of you can take something away from that. And we will still use sentiment analysis as an example when we work with LLMs as well. So I hope this can be useful. Okay, let's get started. So for this, we don't need a lot of libraries. We just need this one library at this time, which is called pandas. Maybe I will zoom in a bit. Okay. Yeah, so we will use pandas for this, which is just going to help us with data manipulation. And you also don't need to download any type of data set. This data should be available because it's been uploaded on GitHub, and then you can use it directly from GitHub. And I won't go into too much detail about this data set, but it's essentially a sentiment analysis data set that some researchers created and made publicly available. And so it's a Twitter data set from quite some time ago, and it was manually annotated. So you can see some tweets over here and the corresponding sentiment label. And so the first few bits of the notebook is just exploring the data where we can see the distribution of the sentiment. And so here we see that there's a lot of neutral and positive content, but not a lot of negative content. Apparently, that used to be the case on social media. I don't know if that's the case anymore, but yeah. And then here we can see that we have like some 9,000 tweets over here. At first, we do a bit of like tokenization to break our data into tokens or word-like bits. So this is an example. And we specifically use a tweet tokenizer here because social media is a lot more noisy than regular human language, right? Because it has these um, slang terms as well as hashtags and emojis and so on. And basically, we need a special tokenizer to be able to deal with this. And so that's why we use this tweet tokenizer from a package called NLTK. And so we apply this on our sentiment data. And then we also create some functions to see how many links are in my data. Again, this is just to explore the data a bit and understand its characteristics. And here we can see that at least like amongst the first five, only the fifth one has a link in there. And most instances don't have any links. And then there are some 25% of the data which has some links, and then some that have two. And here you can also try to do a few things yourself. For example, see the number of @ mentions in the tweets, right? Because these could be useful features for sentiment as well. Potentially, if something has a link, it could be a news article, in which case probably the sentiment is neutral, for example. But yeah, that stuff is a little bit of a side quest that we are not so interested in, but we are more interested in the bag of words representation that I mentioned in the slides, right? So we will try to make this bag of words representation ourselves over here. Has anyone faced an error so far? Okay. If not, then let's keep going. That's good. So we don't want to create this bag of words representation by hand, right? Like looping over our tweets, finding each and every word and then counting them through some type of loop, right? That would be very tedious. And so we have these packages in Python that make this stuff easier for us. And so sklearn, which is short for scikit-learn, is still a highly popular. I'm sorry, I'm getting a lot of messages. Hopefully that's the last one. So scikit-learn is this machine learning package that is widely used, and we can use that for doing this type of bag of words representation creation automatically. And to do this, we need a count vectorizer object. So here we're just initializing this. If you're not super familiar with Python, don't worry about that. You can, of course, always read this stuff up. But essentially, the code that I have here is as simple as we can keep it, that you can still run some of this stuff. But of course, if you have any questions, just feel free to type in the chat or raise your hands and let me know. Okay, so what we are going to do is that we are going to take our sentences, so that's this text part of our data set, and convert that into this bag of words representation. And that is what's happening in this step where we do vectorizer.fit sentences. And then we can see the length of our vocabulary, which is that 9,000 tweets gave us something like 23,000 tokens. And so this piece of code should throw an error. This is on purpose because the idea is that we want to inspect what type of content is in our vocabulary. And again, I told you that this data is from 2016, right? So it totally makes sense that LLM is not there in the vocabulary. But for example, we could see something like gas. And gas should give you the right answer. Maybe you can try this with different examples. So I just changed LLM to gas. It could also be something like dog over here. Child, maybe. And yeah, try it out with a few different examples and see which words are there in your vocabulary and which aren't. And then we get an output over here. So child gives me the output 4,376. You might be tempted to think that this is the count of how many times child occurs, but that's not the case. This is supposed to be the index of where child occurs, right? And this is actually alphabetical, which is why if I have something like the, it's going to be much farther down, right? So this also kind of tells you the internal representation of this type of data. Okay, so then we have our vocabulary, and we can now use this bag of words representation to do stuff later on. So again, we have 9,000 tweets and 23,000 tokens. We need to convert this into an array. so that it's easier to deal with. And here, what we can see is that a lot of it is empty, right? Like a lot of it is zero. And this is the fundamental problem about working with text data. So if I have a vocabulary size of 23,000, just think about a tweet, which used to be at least 280 characters or something like that. And that's probably not going to exceed 40 words, right? So it cannot be that a single tweet is going to have so many. So at max, it's going to have 40 or 50 words. And so in that sense, this is a very inefficient representation because it takes up a lot of data. We don't care about order. So it's taking a lot of space. It's not taking into account any type of context. So it's a pretty inefficient representation, but we will at least still see what results we get from a baseline. So now we have a representation, but we need a classifier now, right? And I told you that we need to also validate this classifier later on. So that's why we need a train and test set. So that's why we're going to use this train test split functionality to create a training and test set. And so that's what happens in this step where we basically put in 30% of the data into our test set and the rest is in the training data. And this is totally disjoint. And so now we have the content or the text part, and then we have the labels, right? Which is the sentiment. And we do this twice because first two steps are for the training set and the next two steps are for the test set. Okay, now let's actually create this bag of words representation because again, this was just to serve as an example. Here we actually create the bag of words representation for the train and test set, right? So here we do this step by feeding our X train to the vectorizer, and we end up with our vector representation. And we also do the same with test. Here you might see that we are actually using two different functions. So for the first part, we use fit transform when creating our bag of words representation. And here on the test set, we just use transform. So maybe you can think about why this difference. This is on purpose. These are not the same things. And it's a subtle difference, but it's very important. And yeah, if some of you have an intuition about why we do that, maybe you can write that into the chat. And I'll let you know before we go into the break. Right. So now we have our we have transformed our text into our bag of words representation, and we can finally create a classifier. And so the nice thing about scikit-learn is that it makes a lot of different types of classifiers available. We are going to use something called a support vector machine that used to be very popular before deep learning came out. And is still, in fact, quite competitive, as we will see. So we use the linear support vector machine classifier, and we create this classifier, and we feed in the xtrain and the labels from our training data, right? And so our classifier has been fit in this case. And that didn't take so much time. And you will contrast this when we actually start using LLMs, that this was pretty instantaneous. I think it took like 10 seconds. And you will see that when we use LLMs, the difference in the time. And now we can use this classifier to predict on our test set, right? So that's our test set right here. And we get the predictions, and we can see what the predictions look like. So here we have the predictions, and here we have the actual labels from the test set, and we can see at least the first one seems to be right. The second one, not really. The third one is right. The fourth one and the fifth one is right as well. Okay, but let's try to do this a bit more systematically. Okay, so we should go into a break in 5 minutes, but let's try to finish this first. So here I have an anti-tweet which just says that, like somebody called Tom is an idiot, and we will see what the classifier predicts for this. So for me, it predicted neutral. Um, this might be different for you. And those of you who are actually following along and trying this yourselves, I'm curious to know if some of you got neutral, positive, negative, especially if you got positive, that would be curious. But this is totally natural, because the thing is that these classifiers are highly stochastic, right? And their behavior can vary depending on many factors. And here, one of the fundamental factors is this train test split, about how we split our data. This is random, so this is not in an order. So that means like my shuffle of the train test split might not be the same as yours. And in fact, if I do this again, my classifier might change. But the hope is that overall, this still gives results that are repeatable. So that's why let's try to do this evaluation a bit more systematically. Um, and so now we're going to use the whole test set and try out some of the metrics that I had mentioned before. And so we're going to use this classification report functionality, which is nice because it gives us a lot of different metrics. So some of you mentioned precision, recall, there's F1 score and accuracy. So this is nice because it tells me the precision for negative, the precision for neutral, positive, and so on. And then we have an overall score as well, right? What about this score? What did you get for your accuracy and macro average scores? Is that comparable? Usually it's between.
Hopefully not having new. Maybe following in Google Meet class fee.
Okay. Um, so what type of results do you get over here? Usually when I've done this with other people, it's been between 55 to 60. And I'm curious to know what results you get over here as well. Um, and yeah, I'll have a quick look at the chat. Okay, at least some of you got positive. Lots of negatives, similar results, but with slight differences, right? So you can see that again, there's a bit of stochasticity here. So in terms of like best practices, the idea is to do this type of classification several times and then report the mean, but also the standard deviations, right? So that we have some notion of the stability of the results as well. And then after this, in the notebook, we also have some results about looking into these results more deeply using something called a confusion matrix, which tells you how the predictions and the true labels compare, right? So here we have the true labels, negative, neutral, and positive, and here we have the predicted labels. And basically here we can see that for positive, this worked out quite well. For neutral, it worked out also well, but at least for negative, we see some issues, right? So it seems that like a lot of negative instances were labeled as neutral, which some of you also saw happen in your example, right? So this is far from being a perfect classifier. And many people already think that sentiment analysis is kind of like a more easy task. And so in that sense, probably a 60% macro average score is not super great. But it still shows you that you can create this classifier pretty quickly using this highly basic representation. Okay, Now maybe I will take a quick pause here to see if there are any questions so far. Okay, you can also type in the chat if you have any questions. Maybe I'll just quickly go back to this point about fit, transform versus transform, right? I think some of you also mentioned this or answered this in the chat, but basically the idea here is that when you're creating this bag of words representation, your vocabulary should only be restricted to the training data, right? Because the test data is supposed to be unknown data that the classifier has not been exposed to. So any new words that come up in the test set should be treated as unknown words because in the real world, you won't have a labeled test data set, right? Your real world application is going to have a lot of unknown text with a lot of unknown words. And so you should be able to see that your classifier, which has been trained on the training data, can still work there, right? So that's why it's important to use transform for the test set and fit transform for the training set. Okay. So I think we can have a short break right now.